Folks, we're going to talk about solutions and concentration, which is a really active area of research, really fascinating stuff. It's a dynamic sort of molecular process that you probably don't think about much, even though it's something that happens very much in your life. So let's dive in. We're going to take some notes, and I'm going to start with some vocab. So, for starters, definition. What do I mean when I say we're going to talk about solutions? What is a solution? Well, I'm not talking about the solution to a math problem, right? A solution is one substance dissolved in another substance, okay? So when you make Kool-Aid, right, you just made a solution of sugar, water, some flavoring, some coloring. There are other solutions that you don't think about, though. It's not always like salt water is a solution, sugar water is a solution. Usually when we think of a solution, we're thinking about dissolving a solid inside of a liquid, but it can be anything. It can be solids, liquids, and gases. Okay? For example, Kool-Aid, right, salt water, but also the air. The air around me right now is a solution because it's not all one substance. Most of the air is nitrogen gas, but there's a little oxygen gas mixed in with it, okay? So that's a solution of two gases. You can have solutions of solids, like steel, for example. I don't have an example of steel around me to show you, but steel is the most common metal that we encounter. And steel is not a pure metal. It's not a metal element. It's mostly iron, but there's some nickel, sometimes some chromium. There are other things mixed in with the iron, and that's a solution, okay? So we're going to be talking about solutions the entire unit. That's probably the most common word you're going to see this unit. When you hear the phrase in solution, so if I'm talking about, I need 10 grams of salt in solution, I mean that the salt is dissolved. So there's some common language that we run into. Now, what does the dissolving? When you make a solution, the thing that there's more of is called the solvent. So if I'm making that solution of Kool-Aid, okay, the solvent is water. If you make salt water, again, the solvent is water. And in the air, the thing that there is the most of is nitrogen gas. So in air, the solvent is nitrogen gas. Whatever there is the most of, okay? Solvent is the biggest part of the solution. This is the abbreviation for the word solution, by the way. I was just running out of room there. Now, what gets dissolved, that's the opposite thing, is called the solute. So in our salt water, remember the water was the solvent. The solute is the salt. In the air, the solute, one of the solutes, is oxygen, because most of the air is nitrogen, a little bit of the air is oxygen. The oxygen got dissolved in with the nitrogen, okay? I shouldn't say the solute because air actually has lots of things dissolved in it, so I'll say O2 is a solute, okay? So those are our main vocab words that we're going to use in this unit: solution, solvent, solute. There's one more, and that's a verb that you might hear occasionally. And it's the verb for like the process of dissolving something. When you mix sugar into water, what you're doing is called solvation, okay? It is also called dissolution. Both of these words mean the same thing, okay? And that is the act of dissolving a solute. And that should get us started. So let's take a look. I have some visualizations up above. What we really want to understand in this chunk of notes and in this topic is, okay, we got the vocab down. What exactly is happening when you make sugar water? When you dissolve something, why does the sugar actually kind of disappear and float into the water? Like, why does it actually happen? But if I put gravel into the bottom of a glass, you know, like little rocks, they don't dissolve. They don't float into the water. They just sink to the bottom. Why doesn't sugar do that? Why doesn't salt just sink to the bottom, right? Why does it dissolve? So I've got a few visualizations here that hopefully can help us understand what's going on. Now, as we know, in a solid, the particles are very attracted to each other, right? There was always, from our prior videos, there's always this fight between kinetic energy and the attractions between particles, right? So here's a solid right here. And you can see these green particles are very attracted to each other. They're not moving very much because they don't have very much kinetic energy. But if I throw some water in here, things change. Now, as you see the water molecules touching these green particles, they start to kind of carry them away. So you see, for some substances, when you add water to the solution or to the solid, it changes the environment, right? Suddenly, there are other attractions happening, like between the water molecules and the green particles. And those attractions between the water and the green particles are stronger than the attractions that the green particles have for themselves. So the green particles, they're still attracted to each other, but they like the water molecules even more. And so that's kind of why some things dissolve and other things don't. If you have a substance where the particles of that substance, like these green ones, are very attracted to the solvent, water is the solvent here, right? Then the solvent particles can kind of carry away the particles of the solute, okay? So let's go ahead and write that down. I'm going to stop this simulation. And the more that mixes together, right, the more the solute particles, like the sugar, it just kind of starts to disappear because the little sugar particles, the sugar molecules, they get spread out in between the water molecules, right? They separate, and they no longer act like a single solid, okay? So, here's our big idea. And I'm only talking about solids dissolving in liquids here, right? This same sort of reasoning applies when we're talking about different kinds of solutions, like liquid in liquid, or gas in gas, or solid in solid, you know what I mean? So when solid particles are more attracted to the solvent particles. Then the solid will be dissolved. A little sloppy there, sorry about that. So kind of how that looks is solvent particles carry away the solute particles. I'm going to add here that the solvent particles separate solute particles from each other. Let's go back to our examples. Sand and gravel. I put some sand in here. It does not dissolve. Why not? Well, you know what? The particles in the sand are more attracted to each other than they are the water. Those sand particles are not very attracted to the water particles. So the sand particles prefer to stick together with each other instead of floating away with the water. And so it doesn't dissolve. It stays in the bottom of the beaker or my Nalgene or wherever you dump the sand. Okay. You might be wondering, and this is where we're kind of going with this, can you predict that, right? How do you know whether your solute particles are going to want to dissolve or not? Can't you know that ahead of time without having to test it in the lab? Well, yes, you can. Okay, and here's where a last concept comes in called polarity. So I've got another visualization link up here. I think it's my third one. Here it is. And this shows us about polarity, okay? Now polarity has to do with when there is a charge difference between one side of a molecule and another side. So on the left here, I've got a bunch of molecules and I have turned up the polarity to very high. These ones on the right that are gray, they have no polarity. Polarity is set to none. So you see the particles on both sides of each molecule are the same. So there is no front and back to this molecule. These molecules over here with the pluses and the minuses, those are called polar molecules because there is a front and a back. There's a plus and a minus side and they are different. And we know from earlier that opposite charges attract. So you can see that the particles here are lined up so that the opposite charges are close to each other. There's always a plus, then a minus, then a plus, then a minus. Those opposites like each other a lot. That's a strong attraction. Now if I hit start and get this wiggling, by and large, these two different sets of particles are not going to mix into each other, right? They are different. The gray ones are nonpolar and they like each other. You'll notice they're sticking to the plus and the minus particles too. They like those too. There are attractions between them. But you see, the polar molecules with the pluses and the minuses, those polar molecules are really attracted to each other. So you see the different liquids we have here are kind of sticking together with themselves. They're not mixing very well. This might be like water and oil, right? Water and oil don't mix very well. Well, let's reset this. And now what I'm going to do is I'm going to make both sides polar. So I'm just showing you both of them are polar now, but I'm going to get rid of the shading so that you can see the difference between the two sides. And you'll see now that since both of the molecules on both sides are very polar, they're very strongly attracted to each other. And the longer I wait, the more they are going to really kind of mix in with each other, right? So I'm fast forwarding here. And they are mixing very well. Again, I will redo that. so that the green ones are nonpolar and the purple ones are very polar. They are unlike each other. And if I fast forward here, see, they really don't mix a whole lot. They stay clumped with their own kind when they're not alike. So we see that we're kind of coming up with a rule here, right? Like dissolves like. Now if I make both sides nonpolar, right, you will see now they will mix together. If both of the things you're mixing are polar, they will dissolve. If both of the things you're mixing are nonpolar, they will dissolve. If one is unlike the other, forget it, okay? Won't happen. So that's interesting. And again, it all has to do with these attractions between particles. Polar particles are very attracted to each other, and so they stick together. Nonpolar particles are attracted to everything, right? So that if there's two different nonpolar liquids, they'll mix. That's fine. But if you've got a very polar liquid next to a nonpolar liquid, well then these polar ones, they really stick together. They never want to separate from each other, so those two liquids won't really mix. So how do we predict it? Let's throw it in the notes. I'll actually write that question out. How do we predict? And the rule is like dissolves like. Okay. Polar plus polar. Nonpolar plus nonpolar, as long as what you're mixing, the two different substances, are like each other. Okay, but not polar plus nonpolar. I hope I made it clear. I'm not sure that I did, but just to wrap this up, what I might have missed here is polar is all about two different sides to a molecule, right? The charge in the molecule is not distributed evenly. So the polar molecules are the ones with the plus and the minus side. Nonpolar means the molecule is the same from all directions. The reason it's called polar is because it's kind of like the Earth, right? The Earth has a North Pole and a South Pole, and they're different. You can tell the top of the Earth from the bottom of the Earth. The Earth is polar. Okay? Nonpolar, you can't tell the top from the bottom. You can't tell the left from the right. It's the same in all directions. Okay? Well, this is just a brief introduction to the main concepts. I'm not going to dig in any further right now. You'll have to go to the next video to find out that stuff. At least just reviewing here, we got some great vocab. We got a visual on how dissolution happens, how solvation happens, and we understand that it has to do with attractions and charges, right, and polarity, okay? And there we have it. Have a good day.